Okay, so let me just say that, so just for the start of the recording, let's just say that this is advanced culvert modeling for Flow2D using QGIS and the plugin. So I've got this project right here, and every structure is already in it. Every culvert is already in it. So what we're going to do is we're going to focus on what you might need to do additionally to get these structures to run correctly. And let's just start with a handful of these structures to just see what they look like and what we can do to set them up or to make sure that they're getting the right information. So first thing I'm going to do is take our elevation data, and I'm going to modify this elevation data so that it has the hill shade so that you can see the elevation. So I'll double click the elevation data, which is LiDAR data, so it's really good elevation data. And we're going to change it to hill shade and click apply. And now you can see pretty clearly the some of the issues you might have with the location of a hydraulic structure. Okay, so hydraulic structures are typically culverts, and culverts typically, have a head wall and an invert. So they're always a location on the map for your grid. This is a 30 by 30 grid. So the location on the map is always on an interface between two elevation data sets or two elevations. So one would be the basin or the invert of the structure of the area coming into the structure, and the other one is the elevation of the head wall surrounding the structure. So if we use the ID tool, it's pretty obvious. It becomes pretty obvious that we have 1425 as our base elevation and 1430 as our wall elevation. Obviously that goes all the way up to 1440 at the top of the wall, but for this grid element, the elevation that was used to define this grid element is a combination of those two. So now if I use the grid ID tool, you'll see that that elevation is an average of all of these pixels in here. So it's not going to be the invert of this structure, but we need it to be the invert of this structure. So what we want this to be is the elevation of 1425.76 or whatever. We'll just use this elevation right here. And I'm going to go ahead and take a elevation polygon, and I'm going to add an elevation polygon so we can correct the elevation, the invert elevation at our structure. So this is kind of common with type 4 inlets and culverts, because they always are on that, they're always perfectly located in the wrong location for good elevation. So we'll just add a little node. What we want to do is just cover the centroid of this cell with a polygon. It could be a triangle, it could be anything, it could be any shape. Actually, the easiest is just to do a triangle that covers the centroid. And we'll call this a culvert or head wall correction. And we'll put the elevation of 1425.76 or 0.77, which is what I got off of the of the elevation raster, the LiDAR. Or you could even get that off of the as-build for that structure, because we want that to turn on. We want this structure to turn on when the water gets to this cell. So we don't want that cell to be higher than the bed of the basin coming in. We want it to be at the invert of the structure. And this needs to go to grid, and this can be empty, and we'll click OK. And now that one is ready for the correction. The downstream side, you could do the same thing, or you could just hit the ID here and see that that is the 1421, and this one is 1423. So that's fine. You don't need to have that lower. That can be fine. or you can do the same thing and you can add a corrector to it. But the downstream in this basin's not as necessary because there's not really any chance for that. This is definitely head water controlled inlet, so there's not a whole lot of chance for this to have a tailwater issue. So we can just leave it as is, or if there is an opportunity for like a tailwater control, then you would want to set that to the right elevation. But because this basin is so much lower than the upstream side, there's not really going to be an interface or an interference of tailwater for those two. So everything else about this structure, let's go ahead and just take a little bit more of a peek at this structure and see something that else is interesting about it. And what I'm going to do is get over to this structure and zoom in on the upstream side of it so that we can kind of get an idea of the detail of the structure. So you can see that it has a trash rack and it has a wing wall, but this one has a rating table, but you could put this in as a rating table or a generalized culvert equation. So this one has a rating table because it was put in using HY8. So they calculated the hydraulics into a depth to discharge rating table using HY8, or you can put it in as a generalized culvert equation. And let's just look at some of the elements of a generalized culvert equation. So what we have is 3 barrels, and they look like they're probably 48-inch barrels. So 48-inch barrels with a 45-degree wing wall, culvert, a concrete apron, and they have 3 of them. So if you go to QGIS and you look at some of that data, let's just grab that culvert in the structure editor, and that is culvert number 9. I have that turned on because I have one of the, from my original culvert data, I have the name of the structure turned on as a label. And it shows you how to do that in lesson 1. So then I'm coming in here to culvert 9, and it goes floodplain to floodplain because that's not a channel, and it gets a rating table, and then this rating table comes from HY8. But if you wanted to turn that into a generalized culvert equation, just for the sake of, simplicity, because it'd be easier, then you wouldn't have to run it twice in 2 different programs. That'd be pretty easy for this one because it'd be an excellent candidate for a generalized culvert equation. So in that case, you'd have a generalized culvert equation, and the box, it is a, let's see, those were round. So that has a culvert diameter in this case of 48 inches, so 4-foot diameter. And the length, you would grab that length very easily just by measuring it here. So I'm using the measure tool that I got from right here. Make sure it's set to feet. And then you can just zoom, or you can zoom in on your map and you can pretty easily pick up the start of that culvert and the end of it. And you see that you have about 252 feet. So that can go into here to 252. And then the type of the culvert, I'm going to get here to the back here to the tutorial, because it has complete the structure data. Okay, it has your type. So here's the type. So the type 1 is box and type 2 is pipe. So if you go type 2, so this is 2, and then you get, this becomes your diameter because it's circular, and you do not need to apply this because it's not going to use it. So then your entrance type, if you go back to this guy, you can see that your entrance type is based on square edge, socket end, or socket end projecting. Well, actually, it looks like it wanted us to apply a box culvert. So it's definitely, we'll just say it's a square edge. We'll just say type 1 square edge with head wall because it doesn't have the flare. So we'll put that in as 1 as well. And your end value for the structure, if that's corrugated, it's like 0.02. If it's just a steel pipe, it's probably 0.01, probably 0.015, 0.015 or 0.018, whatever. Whoops, sorry. And then the K rate comes from the hydraulic design of the culvert. So for a pipe, and let's say that it's not projecting, it's a square edge, so it gets a 0.5. If it had any kind of grooved end or any kind of rounded or anything like that, you might try a 0.2. But if we have a 0.5, it's pretty certain that that is either concrete or steel entrance right there, you know, based off of our imagery. So 0.5, and this can be just 0 or leave it alone. And there are 3 barrels in that one. And then that one would be ready to go. That one's ready, but we already had the rating table for it. So I'm going to put it back to rating table. But that's how you would do that as a generalized Culvert equation, or you could do it as a rating table. So we have it as a rating table. So this data will be written instead of the generalized Culvert equation. What else is important about this culvert? Oh, let's talk about how this rating table works. So basically, as the water comes down into this basin and it fills this basin, as soon as it gets on this cell, which we will have corrected the elevation of this cell by the end of this lesson, as soon as the water gets onto this cell, the control will be, as soon as that water gets up to 0.2 feet of depth, then 1 CFS can go through the structure. At 0.1 feet of depth, 0.5 CFS can go through the structure. So if your data is in the English system, this will be depth in feet, and this will be data in cubic feet per second. And if your data is metric, this will be depth in meters, and this will be CMS, cubic meters per second. And it's basically a linear interpolation between these data points. So something important about this is that you need more data down here where it's non-linear. And then up here where it gets relatively linear, you can have less data. So you need more data down here where it's non-linear. So because we do a linear interpolation between the 2 points. So if you have data down here that's non-linear, you need more points in your table. And then up here doesn't matter so much. Now, what do you run this up to? Well, basically you run it up to the, like, let's just, in this case, it's obvious you just want to fit, if this structure is full of water, then we have that pressure flow through the structure to the downstream side, then we want to at least run this up to the top of this roadway. So let's take a quick look at that change in elevation. Let's go ahead and get back on our ID tool and make sure that we're back on our elevation. So we have a change in elevation of 1440 down to 1425. So we want at least 20 feet in here. So this one goes up to 18, so that's probably just fine. What else do we need to know about this? Let's talk a little bit about the head reference elevation. So in this case, my head reference elevation is 0, meaning that it's not used. Not that it's 0, but that it's not used. So what is a head reference elevation? So our elevation up here is 1425.7, I think is what we set this to. And so the head, as the water gets onto this cell at 1485.7, which I think is what we assigned to our elevation right there, the structure will turn on. However, if there's something preventing this structure from turning on, like a weir or something, like maybe a trash rack or a debris riser or something like that, that's a different elevation than the invert of the structure, then that is your head reference elevation. So usually you'll leave it off, so you'll leave it at 0. But if you have a head reference elevation that is different than the invert of the channel, such as a riser or maybe a weir or something that stops water from entering that structure, then you'll use that as the reference elevation for the structure. So typically you don't want to use head reference elevation only if you have some kind of control that limits that. Let's see. And then if it's a structure that's, say, less than 500 feet, you don't need a conduit length because you don't really care about the travel distance time and the volume of this structure. It's negligible compared to what's happening within the hydraulics of the basin. The travel time and volume of this culvert is negligible. So you don't have to worry about accounting for that. So you can just leave these two at 0 for a rating table. If it's a generalized culvert equation, you need them. For a rating table, you don't need them. Also, another thing you don't need, and it's written as 0, is unless you have like a culvert that's, say, 1,000 feet long and you really care about the travel time and the volume in that culvert, then if you do care about that, then this would, go up to 1,000, and then this would be the diameter of the structure, which would be, well, I think the diameter of the structure would be, in this case, 4 feet. And then you would need this volume rating table. So this is like what is the volume of that pipe at 0 feet of depth? The volume is 0. At 0.2 feet of depth, what is the volume of that pipe that is taken out? And that's what this area rating table is. This is like an area at that depth, a cross-sectional area at that depth, and that will help take that volume out of the system and leave it in the pipe as the water is propagating through the pipe. Typically, we don't use it, and I don't really recommend that you use it unless you have a really long pipe. Okay, so I'm going to turn these back off just so that we have those at 0. I just wanted to let you know how those work. And we won't do this for every single structure. Every structure has some different elements that are important. So that's pretty much all the detail you need for this structure. Let's go ahead and move on to the next structure and just take a look at it. So the next structure is a floodplain to channel. So you can see here that the type is floodplain to channel. That's important. Let's go ahead and go down to another structure that's channel to channel. I think they're down at the bottom. Okay, here's one that is channel to channel. And we'll get to this later. We'll get to this in a bit, but channel to channel is basically always assigned to the left bank. Yeah, we'll do this one now. So always assigned to the left bank. And what's important about these is that, well, you can do these a couple of different ways. So one of the problems, if you see in this project, I stop my channel right here and I start up another channel segment downstream of the culvert. Now, lately, I haven't been doing that because I've kind of come to the conclusion that it makes it more difficult to review a channel. So lately, what I've been doing is just running that through the whole way and then just putting no exchange nodes right here so that then my inlet goes here, my inlet of the structure goes here, my outlet of the structure goes here, but these internal nodes are no exchange nodes. And that seems to be working better for hydraulic structures and channels. But in this one, I just split it up. I stopped my channel upstream of the structure and I started it back up downstream of the structure. And so the elements that are important on this particular structure is that it needs to be set to channel to channel. It still has a rating table because, again, it came from HY8 because when we built this, the generalized culvert equations were pretty new. So we just went ahead and put these all in as rating tables. This one actually could use a tailwater control, but I always start, unless I absolutely know the tailwater control for this channel needs to be turned on, I typically always start with tailwater set off and let the model tell me whether or not it needs a tailwater control. So this always has to be set left bank to left bank because it's not assigned to the grid element, it's assigned to the cross section. And if you look right here, this is the cross section for this channel. This is your cross-section station elevation data. So it defines this area, this cross-sectional area that feeds the culvert. So you don't need to do anything on the right banks on this one. It just goes left to left, and it's assigned to the cross-section. And if you wanted to see that in, like the real cross-section, I'll show you. Let me grab this guy again. I'm using this Flow 2D info tool. I'm just going to grab that cross section and I'm going to click it, and then it's going to load it. So as the water comes down to the channel and starts to hit that cross section, as soon as it gets on that base of that cross section, that becomes the invert of the structure. So it starts to fill the channel and fill the structure, and the structure, the station elevate, or sorry, let me get back to that structure. The rating table, as the water gets up to 0.1 foot of depth, then 2 CFS can go through the channel, or can go through the structure. So as the channel gets up to 1 foot of depth, 124 cubic feet per second can pass through the structure. Now, the things that are important about these channel ones is, one of the things, the common mistakes people make is that they don't account for this expansion right here. And so they'll apply the rating table for the structure, which is clearly much bigger than, your general channel geometry, which is right here. Let me go ahead and grab one of these guys. So you can see that this is a lot different geometry than this one. This one is wide and almost rectangular, and these ones up here are relatively trapezoidal. It's actually a gabion bank, but it comes in as a trapezoid when you interpolate it. And so these are relatively trapezoidal coming down here. And so if you don't account for this expansion right here in your cross sections, your rating table is going to take way too much water at the early early depths, and you're going to end up with, when the structure takes too much water through the structure, then it reduces the stage or the depth up here too much, and then you start having surging. So if you see surging at this cross section, or surging at this cross section as the water is propagating through this channel, if it starts to surge, it usually means that you didn't account for the change in the cross-sectional area as this channel transitions into this structure. And it transitions even worse as it comes out. So you need to really set this up to kind of match the physical system. That's kind of one of the biggest problems with setting up channel hydraulic structures. And Jim has an excellent presentation on this. So if you go to our hydraulic structures presentation on my website, Jim has a great explanation of how to set these up correctly. All right, let's close this up and let's just review other issues that you might have with this structure. So tailwater effect, if you leave it to no tailwater effect, the hydraulic structure warning data will tell you whether or not you need it to be a tailwater. We can actually look at that right now because I have this run. Whoops, wrong one. So I have this run. So we have a file called, well, you can do error.check, and then I don't see any issues with the structure. I think that this is basically a warning about the fact that you're using I think this is a warning about how the channel transitions from the upstream, or from the end of the channel or the terminus of a channel to the floodplain. I don't think there's actually any errors. So there's no errors here, but you will get hydraulic structure warnings, and it'll tell you what you need to do. So it says the rating table for the Greenway was adjusted to better match the stream flow conditions. Well, so what's happening in Greenway 2 is that, let me show you, this is Greenway 1 and Greenway 2 are basically the same. So it's telling us that the rating table might not be correct, but really it's not the case, because what it's saying is that the water coming out of the channel is accelerating. So the water that's going into the channel and the water that's going out of the channel it's not causing like a backwater condition. So the flow is accelerating away from the structure. Well, if you kind of look at this structure, that's exactly what's happening, because there's a huge drop right at the downstream side of it. And that's why I don't turn the rating table, the tailwater switch on in this structure, because it falls away from that side of the channel. The same thing on Greenway too. It's the same exact thing. See, it falls away from the structure and moves downstream. So it's a headwater controlled structure. So I don't set the tailwater condition to tailwater control, and I ignore this message. So if you use that tailwater condition to no tailwater control, then this calculation adjustment will be suggested, but it won't be used. Anyway, so we're not going to change the rating table. We don't have it. We also didn't get a warning about the headwater, or sorry, about the tailwater being higher than the headwater. So we know we don't have to use the tailwater condition in this particular structure. Okay, what else happens on channel structures? That's about it. That's about the only things that go wrong on them. Now let's do another different kind of structure, a floodplain to channel structure. So let's go ahead and look at maybe number 70. So number 70 is floodplain to channel, meaning that it is going to pick up the water from outside away from the channel and direct it toward the channel using a rating table. In this case, it's a rating table, or a generalized culvert equation would be fine too. So let's take a quick look at this from the perspective of like the maybe, so it looks like what we have here is a little basin. And we also, as you can see, not only do we have a basin, but this one might be a little off. Like we might want this inlet to be here, because it looks like it's really more assigned to the road. So let's fix this one. And not only are we going to fix it, but we're going to maybe give it an elevation polygon as well. So how do we fix it? It's pretty simple. You go to structure lines and you hit edit, and you hit the node tool, or the let's see, vertex tool. I think in ArcGIS it's called a node tool. In QGIS it's called a vertex tool. Let's just move it a little bit. And let's also, not only are we going to move it, but we're also going to add an elevation polygon the same way we did before. So let's grab the elevation map, and we'll ID the elevation. Wait, I need to be on the layer. The elevation is 1401. So let's go ahead and put an elevation polygon in here. And again, remember, all it has to do is cover the centroid and then give it a name. Again, this is a culvert head wall correction. And the elevation is 14. Ooh, that's not how you spell 1401. 1401.98. And the membership goes to grid, and you click OK. And now this will be the invert elevation of our structure. So I'm going to come here and I'm going to click save and turn that off. And then, you know, I'm just going to maybe these guys can go together, and then we'll just go back here. And then over here, because I moved this, I can now hit the schema tool, and it will reposition the schema layer, the inlet node, to a better node, because we don't want it on the street, because then the street, you know, then the flow is coming from the street, not the basin. Another thing about this basin that's interesting that you can do to a basin, if it's a small basin like this, maybe it's not getting the full capacity because it's such a small basin. One of the things that you can do with a basin is you can take, well, we'll show you that in a second. Yeah, let's not go with that. I was going to show you how to do an elevation correction for a basin, but maybe we'll do that later, because let's focus on hydraulic structures. I don't want to go in the wrong direction. Okay, so now let's see. Now the water gets into this basin, fills the basin, and then I didn't want to change the elevation right here, because this grid is more street related. So instead I just moved it and set the elevation to the invert right here. So as this basin fills and the water on this grid element gets up to 0.2 feet, then 8 cubic feet per second can go through this structure. This is also an excellent candidate for generalized culvert equation. I would also say that this structure is, let's take a look at the downstream side of this structure from the perspective of the aerial. So let's just let's move ourselves down there in that direction. Let's see, that's Grover Basin. Let me get us down here to our channel. And wait, hang on a sec. I'm okay, I see the problem. I'm in the wrong direction here. Okay, now we're going to get us down here to our channel, which is, I gotta zoom out a bit and orient myself here. So I want to kind of come down to this one, I think, because this will be Greenway 1. And what we have here is not only a huge hydraulic structure coming from Grover right here, that's the outfall of that massive basin, Grover Basin, which we're not worrying about yet, but we also have where's that hydraulic structure? Let's find it again so I can, okay, it's just a little basin. Oh, I'm in the wrong spot. That's okay. That's why we can't find anything. I'm in the wrong spot. Okay, let's go down here to Greenway 2. All right, so, and again, this also has a huge pipe system coming down and outfalling right here, but it also has this little basin right here that looks like it's collecting water from this guy, but maybe just, I'm not exactly sure how that's working, but that's okay. Let's go ahead and take a look, just a peek at this structure and see if we can get some ideas about it. So I'm guessing that is a 36-inch pipe, and I would also guess, I'm not positive about this, that this might just be crossing the street and filling it. There might be a scupper or something along here. Not sure how this little rectangular drainage channel is filling this, and it looks like it also might have a bit of a fill right there. So 36-inch pipe, we know our invert elevation upstream because we picked it off of the elevation data. Now let's see what's happening down here and how is this pipe or culvert pipe connected to it looks like it's coming in right here. Okay, so coming in right here, got a bit of a protective rack so nothing can get into this drainage channel. And the important thing about this structure is that it will be filling there's no change in elevation right here. It's just going to be filling straight into the channel. So let's come back here and let's look at that. So what do we do? What do we assign that to? We don't assign it to the left bank or the right bank. We assign it to the cross section. Okay, so hydraulic structures always go, regardless of what side of the channel they come in on, they're always assigned to the left bank of the channel because that directs them to the correct cross section. Because you can see right here that you can have more than one cross section assigned to a right bank, but you can only have one cross section assigned to a left bank. So what's happening right here? So here's our rating table for culvert number 70, and here is our cross section, channel cross section for this specific cross section. This is the schematized data, not the interpolated data, but the interpolated data. So the bottom of this channel is 1392.33. That's exactly where that culvert was coming in at. I know it was right down here, but we can't have two culverts assigned to the same cell. So we just popped it up a little bit and got it away from that other inlet. Okay, that other hydraulic structure. So it's off. And the same thing goes for a storm drain. So like I've got a storm drain coming right here, but I can't assign it. This one already has a structure assigned to it. So I have to assign my storm drain right here. So same thing here. I have to get it kind of away from that structure, assign it just upstream. And as that water comes down into, or sorry, excuse me, as the water fills this channel, if you use the headwater reference, or sorry, the tailwater reference elevation on this one, if we set that to reduced discharge but no upstream flow, let's just assume that this was a flap gate, and that's why I had that funny looking structure on the bottom of it, that because it was a flap gate. So this means reduced discharge because of the tailwater condition, but it's going to keep allowing discharge through the structure so long as the head right here is higher than the head in the channel. Now, if the head in the channel becomes higher than the head upstream, the discharge that's going through the structure will start to go down due to the submergence condition. So as the submergence turns on and the structure becomes submerged, then the headwater right in this cross section will reduce the flow through the structure based on the pressure head. So it's already automated, and we turned it on by allowing reduced discharge, and we applied a flap gate by saying don't allow upstream flow. If there's no flap gate and you actually could fill this side basin from this channel, then you would choose the next tailwater option. But we clearly, there's not going to be any filling from here to here. And there, to be honest with you, there's probably not even a submergence criteria right there, just because this is so much higher than this over here. So this is very likely headwater controlled anyway. I just wanted you to understand how that works. Okay, let's try one more or couple. Well, actually, I want to try two more because I do have one generalized culvert equation I wanted to show you that's a little bit weird. So let's maybe go take a look at it and see which one it is. So it is number 122. So I'm going to go to Culvert 122, and as you can see, no table. It is floodplain to floodplain because, see, even though this clearly looks like a channel, it's not a channel because we didn't put a 1D channel in place. I see a lot of people who see a culvert that's connected to a channel, but they're not modeling it as a channel, but they still try to put that in as a channel structure. So you only want to model a channel structure if you have that 1D channel in place. So channel to channel, floodplain to channel. Let's go back to 70. See, floodplain to channel. So even though if you're just using the floodplain or the grid to represent the channel, then you don't ever assign a hydraulic structure to a channel unless there's a left bank or a channel cross section defined. Okay, let's go back to this one. That's just a common mistake. I just wanted to make sure and tell that to you. Okay, so let's get back to our image here, and let's make sure I'm in the right direction and get up here to Turtle Basin, because this one's a kind of an interesting structure. Has a lot of weird features here that we are going to need to account for. So first of all, let's take a look at the opening of the structure. And obviously, if you had the as-built, or if you didn't have the as-built and you didn't have a good view of the structure, you'd want to go do a site visit just to get the dimensions of the structure. I have a pretty clear view of the structure, so I can get the dimensions just guessing it, because box culverts, concrete box culverts, are pretty standard design, so they only have so many dimensions, especially if you are dealing with a single city and that city has a hydraulic design guidelines. Then you can go into their hydraulic design guidelines and you can get the standards for culverts. And then based off of this image, you can compare that to their standards and be like, oh yeah, this one's a, 4 feet, maybe like 4x8 or 5x8 or whatever their standards kind of include. So let's just say that this one is, let's see, I don't want to guess. Let me just see what I gave it. I gave it a 5 feet box height and an 8-foot base. And you could also, again, as-built would give you that, or go do a site visit and just measure it, whatever. But that's what you need, just that inlet dimension. There's only one box, so I don't have to put multiple barrels. But there's something funny about this structure. It's got this, I would call this an attenuation basin right here, because it has a control point right here that will slow the water down and allow it to percolate into this, probably some gravel under here that would help, like an LID type of thing, that would help this system percolate and slow the water movement down so that you have less erosion and less water going into the basin. And obviously it is a direct drainage or basin for this huge property development, because this probably just used to be open desert, or possibly a farm or something, that was much different before the development came in. And so this development community cannot increase the water depth on its downstream neighbors. And it can't just rely on this basin only, because this basin was designed for the street flow, not the water flow, right? So if you have a development community, or you're doing a design model, you can't increase the depth or increase the downstream water surface elevation on your neighbors. So they put this basin in, and not only is it related to this development, but is also related to this development too, because all of these guys, all of these cul-de-sacs are going to come right into this basin, and then fill this basin, and then this basin is connected to the downstream basin. Looks like through this is kind of funny, because this looks like it's a bit of a wall with weir, possibly openings in the bottom to represent a weir. It's kind of hard to see it, and you can't get in there but you can see there's clearly openings, and you can see that the water has to overtop this basin before it can share into this basin. So it's all designed per the ADMS, water control and water surface elevation and discharge analysis off these huge development areas. Okay, so what we have to do is figure out how to model this with Flow2D. And so basically the grid can kind of represent this control point, or you can put a little levee in here, or you can put an additional structure to represent the water going over that weir. That's kind of up to you what you want to do. But it's basically just a sharp crested weir that fills this control structure before the water goes into. So it's probably like somewhat of a stilling basin before the water goes through the structure. We don't want a bunch of sand and stuff, because at the bottom of this structure right here is also a storm drain pipe. So it's gonna whatever, or maybe I think it might be like a low flow storm drain pipe. I'm not quite sure, but you might be able to see that there's a pipe network. Like there's a drain right here. This is both an inlet and an outfall. It's an outfall from the street flow, but also an inlet from the basin. So the basin drains this way, but it also picks up the street flow. So if the street flow overcomes the basin, it can pour into the basin and then drain back out. It's an interesting system. So what we have to do is just figure out how to set that up Flow2D. So we come back here, and we see here that our elevation is kind of already in place, but maybe what we want to do is put an elevation corrector here, and I'm going to do something a little bit different this time. So this time I'm going to grab, because I'm going to try a basin control. So this time I'm going to grab this guy, and I'm going to leave this one alone, and I'm going to make my inlet go here. Let's see. Gonna go ahead and follow this basin all the way up. And I'm sure this basin is fine because it's a really big basin, so I'm sure it's fine. To here, and then I'm going to grab it up in here too. And I'm going to apply a basin control. Let's see, let's go like maybe, yeah, here and then here, and then right click. And then we're going to call this, instead of a head wall correction, let's call this a basin correction, just so you can see the process. And I don't need an elevation for this one because it's going to be different. I'm going to assign this to grid and click OK. And then I'm going to click save on that just so we don't lose it in case I get a crash or something. And so what this is going to do is it's going to apply an elevation correction where it takes the minimum of all the cells in the basin instead of the average. And then what it's going to do is it's going to apply the minimum elevation here too. So we're going to get the minimum from our head wall. So that will define our invert. And I'm also going to put a levee right here. And I'm going to define the elevation of this weir with a levee. So I'm going to do a, first of all, I need that elevation. So let me get that elevation using the ID tool. And that weir elevation is 1396.4841. And I'm going to grab the levee line and make a simple levee line right here. Right click it. The elevation is, what did I say that was? Is that 1396.4841. I don't need a correction. I don't need anything else in here. And let's just call this let's just call that the culvert weir. The weir related to that culvert. And click OK. So that the thing is that the head reference, this doesn't like work as a head reference elevation because it's not really associated with the culvert. It's prior to the culvert. So in this case, the culvert will turn on when this grid is filled, and the water will get into this grid when it spills over this levee. So let me save that and just calculate that levee real quick. Let's just see if it set it up correctly. So levee. Okay, that's fine. And we don't want the polygons. We just want the user lines, and just create that. Nope. I need to do that. I need to do this side too. So let me try that one more time. I'll just move it a little bit until we get that. Yeah, there we go. And now this works as a levee, so the water has to overtop it. And this elevation is actually going to be taken out of this grid element and this grid element. Now, let's go ahead with that elevation correction. So what I want you to focus on right now is I'm going to grab the ID of this cell, and you see that's 1392.56. That's your elevation right there. Now let's apply the corrector, but what I want to do first is maybe select this polygon. Oops, that's not how you select it. You select it like that. And I'm going to apply the correction to only the selected polygon because it's going to use a different elevation correction than the others. I guess I could set that other one up like this too. So if you look at the elevation correction tool, it has external layer mode, and we're going to set that to elevation polygon, I think, if I can find it. And we want the geometric predicate to be centroids within the polygon. So the centroids within the polygon are going to identify which grid we want to make the correction to. That's what this is. And then we're going to do statistics within the grid elements, but we're going to take the statistics from the raster layer and we're going to use a minimum. So what it's going to do is a statistical analysis of all the pixels that are inside each individual polygon. And we want the statistics that are inside the grid, not the statistics that are inside the whole polygon. And we only want to use the selected feature. And I don't think this works, so I'm just going to ignore this. Well, and plus I already have that in my elevation polygon layer, so this is just doesn't really work. And then I'll click OK. And what it's going to do is it's going to look at each of these individual polygons that have a centroid within this polygon, and it's going to apply a grid element correction to them to a minimum of the elevations within the raster. So that was 1396.69. Now if we hit it again, you'll see that it's going to go down because it's now taking the minimum elevation of that polygon. And these ones all went down as well. They all went down to the minimum or the minimum of those rasters. So it kind of gives you a control over your basin. Now this one was a little bit overkill maybe because I probably just made this a little bit too much control on this, a little bit too much volume in that particular area. But you can see how that would be helpful and how you could use that to help define your basins or define like little weird things like this that require a minimum elevation instead of an average elevation. And I want to show you how to use that. So now this guy is ready to go. So the water is going to fill this basin. This is your control point because this is an attenuating basin. And so as it starts to flow over this and get onto this grid element, as soon as it starts to overtop this and get into this grid element, it will then flow into the structure. And there's also a control right here that's going to allow the water to get off the street into the structure because this elevation is going to be a little bit lower than the street, which is exactly how this system is set up. It has a scupper and a grate right here and a scupper going into the basin. So there's an opening in the sidewalk right here and a control into the basin. If I can get this, yeah, right here. So that grid element elevation is already allowing, because it's a little bit lower, is already allowing the water to get into the this stilling basin. Okay, let's see if there's one more thing I wanted to show you because there's one more kind of strange area here. So the final structure that I wanted to talk about is this system right here where you have kind of like one outlet and 3 inlets that are kind of funny the way that they're set up. So let's take a quick look at this in the aerial. And let's see, I'm gonna get out of here and go up here to this last example of hydraulic structures. And I'm sorry, I'm gonna go over a little bit on time, but for those of you who are doing hydraulic structure modeling, this is good information and you will appreciate it. But I think I need to go right here. So I have, this is a little drainage channel right here, comes all the way, and then these guys just flow right into it. And as you can see, there's openings in the wall, and they just have these little drainage easements that go right into this channel. I don't have this channel modeled as a channel, so I'm going to show you an easy correction that you can do to get that in there. So all of these cul-de-sacs drain to the basin or drain to this drainage channel. It's just a little rectangular channel. And then they go through a hydraulic structure right here and into the outlet of the structure down here. Then there's some other ones that are connecting to this structure, but they're a little more complicated because there's no little drainage channel because they put this road in instead. So these 3 are connected to this outlet through a pipe system. So you would probably set those up as storm drain, right? That would be like the common thing to do. But if you don't want to just set up a storm drain and you don't want to review a storm drain, you can set these up with a simple storm drain system using hydraulic structure, where this is the outfall for all three, or outlet, let's call it the outlet, for all three of those inlets. Now I'm going to show you a couple of things about this system here. And the first thing I wanted to show you is that we do have, this channel is pretty important, right? It drains a lot of stuff. But we know from how Flow 2D gets its grid element elevation, we know that these elevations are all going to be averaging. And so we're going to lose that capacity. So we either have to put in a 1D channel, or we can just lower the grid element elevation. Since they're all in a perfect straight line, it's a perfect scenario, using an elevation polygon. So let's do that to start with. Let's do that. And that will ensure that anything that connects to this channel, I'm just going to keep it, I just want the centroids. I don't really care so much about the, yeah, that's it. That's perfect. I don't care so much about the, snapping to the grid or anything. I just kind of want to make sure that I get the centroid in this case. So then it looks like, yeah, we're still good. Just going to stay here. I'm going to grab, and I'm going to do this one as well. And then go back up. And grab that here, and then right click. And again, I don't care. I don't need an elevation. This goes to grid. Don't need an elevation because that's going to come from the raster. And this is going to be called let's just call it a Basin Corrector, because it's going to work the same way that the last one did. And just click OK. And then again, I'll just select it and apply the corrector only to the selected one. Okay, let's see. So this goes to elevation polygons. This goes to centroids. This goes to statistics within the polygon from the raster layer. And we want to take, if you uncheck this, it'll take the minimum of everything inside the raster, and it'll apply it to every grid element. So we definitely don't want that. Instead, we want the statistics from the raster for every cell for every individual cell. And then click OK. And you can also do that with a polyline. Like you could draw a polyline along there and it would pick it up as well. And so you can see that we got our central. These are all going to be now corrected. I don't know if we'd be able to see it because, yeah, you can see it. You can see that it's a little, let me turn these off. You can see that it's a little lower. Well, you can't really see it. It's not, there's too much elevation change over the whole thing. But you can see this one was corrected. You can see the corrections here. And so that one will now allow water to get down there and into here. And you don't really have to do that to these ones. Maybe they're not so important, but because the water is going to kind of collect, near these naturally anyway. But let's take it. So that one's ready to go. And then maybe what we want to do here is like another basin on this one. Same thing, just don't necessarily have to go nutso with it. So maybe just right in here. And then anything that is like a centroid in here, same thing. And save. Obviously, I should be doing these multiple, not just, I shouldn't be wasting my time doing them one at a time. I should just do them all at once. So just something you can do. Nope, wrong one. Sorry. I don't know if I used the min. You know what? Hang on. I'm gonna select both of those and do it again because I can't remember if I hit min. The next thing I'm going to do is only show the ones that have data in them. That'll make that easier. that's coming at the end of the summer. Okay. Elevation polygons, centroids, statistics, min, raster, only selected. Okay. And that is good. Now, so now these are the elevations and everything are ready on these three. Let's just look at one final thing. So these three right here have a kind of a special thing that you need to do for them, and that is they need a D line. So what's going to happen is that you're going to have a different inlet identification or grid element for each of these, but they have all assigned, oops, sorry, they're all assigned to the same grid element. And it looks like, let's take a quick look at our grid. Let me turn the elevation off real quick, and let me just unselect everything and turn this off. And then, okay, here's our grid right here. Oh, that's the problem. So here's our grid right here. And let me make sure my polygon covered that. No, it didn't. Did you notice that my polygon didn't cover that? So it's not going to be applied. So I'm glad I did that, because now we can see that. We'll have to recalculate that. Okay, so you see that all three of those have the same cell in the outlet, but it also needs one more thing. And there's a mistake on this one, so you got to pay attention to this. So I assigned the D line to this cell right here. And so I'm going to hit this just in case, because I know we made a change up there. So what this does is it's going to write the storm drain capacity, and I said, okay, give it limit it to 600 cubic feet per second. But if you look at this, well, probably, yeah, 600 is about right, because each of those, the capacity is about 200. And there's probably not going to get 5 foot of depth on that, not even close, because it's just too flat in here. So the limit of 600 is fine. And I basically did that based off of the Q table. And now I'm going to export this into the DAT file to show you the problem. So the way to get this to work is that they're all going to export into this cell here, and they're not going to be able to fill more than 600 cubic feet per second for any given output interval into this basin, which is total overkill, obviously. Now let's see, what did I want to show you? Oh, let's export it. So now that we have these culverts, you just got to make sure that your structure switch is turned on, and then you can export it. So let me just use the export, and want to make sure we go to the right one, the webinar export. I'll select the folder and I'll export the project. And now we can go to the webinar export and take a look at the hydraulic structure.dat file. All right, so this S is a new structure, culvert name. Whether or not it's a floodplain channel or floodplain to channel or whatever goes here. Whether it's a rating table or a culvert equation is here. And again, you can get this from the data input manual. Inlet node, outlet node, that's a grid element. Inlet grid element, outlet grid element, tailwater switch, and then this is head reference elevation, culvert length, culvert width. Then this is your rating table. You don't really need these, but it's fine if they're all zeros, doesn't hurt anything. And then let's go down to the one that has a generalized culvert equation. So it gets its own line right here. And this is box, I think that, I have to look up what that is. That is wing wall flare 30 to 75, which I think is exactly what that is. So let's just double check that down here. Yep, we got our wing. Yep, that's our wing wall flare right there. And where'd that go? And this is your N value. It's probably supposed to be 0.013, but I typically go up a little bit. That is your K, your entrance loss coefficient, which that might not be quite right. So you might want to check that one. That is the width of that box culvert, and there's only one barrel. And then the last two are 129, Greenway, the two Greenway. Oh, and sorry, you can see there was one thing here I missed, 129. So here's 129. Here's the D line. It's in the wrong spot. So I'm going to Control X, and I'm going to get it out of there. And I'm going to take it to, so then you have 129 regular is 12949, 129B 12949, 129C 12949. They all go into the same. So we need the D line, but it has to go to the very end of the file. So I'll have to fix that. The plugin is not doing that correctly. I don't use that very often, so I didn't realize it was a bug until today. So there you go. Just put that at the end and save it. And then this is ready to go. So I think that we can just run it. So if I come here and I click the Run Flow 2D, I don't know if we're going to have any errors or not, but that goes to the webinar export. Click OK, and we might get some errors because of that levy, but everything else should work because I already ran it. But I didn't have that levy the first time I ran it. Oh, no, it's good. Oh, you know what, though? I didn't turn the levy switch on is probably why. I didn't turn the levy switch on, so that's not very helpful. Let's try that one more time. I'm going to export it again so I can get the, well, let's see. I need that levy switch turned on, and I need the levies. So let's export it one more time, but I don't need to export the whole thing this time. I just can export. I just for sure need this, and I for sure need the cont.dat. It's going to go out there anyway, but I don't want to overwrite that culvert. You know, that data that I changed in the highstruct.dat. Ooh, I don't know if that's going to actually allow that to write. Okay, turn off. Let's see if that updated. I'm going to go to cont.dat, and I just want to make sure that that levy switch is on. So channel, street, levy. Yeah, that was it. And then just make sure that levy.dat is in there. So we might get an error if our, oh, you know what? I think I might need one more thing. I forgot one more thing. I might have needed to do a final elevation correction. I can't remember, but oh yeah, I know what it was. There was two other things I didn't do there. I didn't run the correction on the other two because I was going to show you those at the end. I was going to do them all together. So look, if you look at these, sorry about that. I apologize for that, but there's one here called a head wall correction, and there's another one somewhere else. I think it's in that other basin that was right next to the channel. Yeah, there was another one like right here. So we're going to apply that correction now. And so I've selected those two, and this one's a lot easier. You go to grid, you go to this guy, and this time we want elevation polygon attributes, only selected features. So then that will reset those elevations. And don't worry about this. This is because I didn't have any points. I got to get this error out of the thing, but it's just because there wasn't an elevation point in there, and it was assessing, it was looking for it. I don't know why. It doesn't use elevation points, but it was looking for it. Okay, now I have to, unfortunately, I have to export that again, but only the topo this time. So this time I'll go export, and webinar export. I wish it'd just go right back to the same folder, but I don't want that hydraulic structure. I just want the topo this time. And I'll click OK. And now I need to start the run again. But because I changed the elevation, I want to just get rid of these guys. CAD points, F-plane, and Mannings, because I changed the elevation. I'll just get rid of all the output files. That way we know for sure we're running clean, a clean run. And let's make sure we're getting some rainfall data and make sure our switches are on. channel, levee, rainfall infiltration, hydraulic structures, and just run it. And I'm hoping we don't get an error on that levee, but we might. No, we didn't. Okay, so that means our levee was set up correctly because it didn't tell us that its elevation was bad, so it means it's good. That's why I changed those elevations in that area too, so we wouldn't get that error message for that levee. So it's going, and I've already run it, but I didn't have the levee in there when I ran it. I just had the hydraulic structures, but I wanted to run it to show you the hydraulic structure warnings and output data, which I'm hoping to connect to the map this summer. So here's your hydrostruct.out. You know what? I'm going to open these in Notepad or Notepad++ so that we can kind of see them together. And let's get rid of that. So here's your hydraulic structure warning. We already talked about these a little bit. So remember, it's just telling you that the water was accelerating through the structure. So we made it a suggested adjustment to the rating table, but we don't need that. We know that water is going to accelerate through that structure, so we'll just ignore that. And see, but the suggested potential revisions are represented in the data file, but they're not used. Okay. Hydrostruct.out gives you some information for each of the structures. So this one is, let's see, this one is culvert number 9. That was going through the Grover Basin. The maximum discharge was 600 cubic feet per second, and the time was 4 hours. Then you get a time on the left, discharge on the right. And if this is negative and this is positive, that means water is flowing through the structure from upstream to downstream. If this becomes negative and this becomes positive, then that means that, well, this wouldn't be anything. This means that the water would be going backwards as a backwater condition through the structure. If you start seeing things like, let me get this fixed. If you start seeing things like this, negative to positive, you could have a tide condition, or you could have something wrong with your control at the outlet. So if this is going negative, positive, it's because it could be because of a tide. What's this one? Culvert 069. This is floodplain to channel. Don't see anything really wrong with that. Quite a bit of water going through it, surprisingly. And then what you could do is you could take each of these structures, these output conditions, and like you know the structure or you know the inflow node. So if I hit Control C or I know 069, then I can come back here and I can put this either to 069, but there's probably going to be a bunch of them, or I can put this in here, the grid element inlet node, and I can just zoom right to it. Oh yeah, there's probably going to be a lot of water coming through there. And this one might have a tailwater control, so you might want to set this one to reduce discharge. Even though it didn't tell us that it had a tailwater control, it might. And the arrow on these structures, the green arrow, shows you the flow direction. So this is the circle, and this has the arrow, so that's your flow direction. What else is in here? Oh, and then flow through the structure is also kind of, flow through the structure because there's a channel is also kind of represented by the HighChan.out. So if I go down here to the very bottom and I've got my greenway structures, they look pretty good. I think I put 100 CFS into that, but of course there's also outside water coming into that channel as well, like rainfall and other structures are filling it. So I think I gave it a steady state of 100 CFS, and then there's some other structures filling it. Although, I'm surprised to see almost 500 CFS in there. And then you come here to HighChan.out. What we want is this number right here, 35368. I'll just do a Control C, Control F, Control F. It's over here. And then just put like a space on that. 35368. Hang on. 35368. Okay, maybe it. Oh, okay, there we go. So this is that channel that's feeding the hydraulic structure. So you can see as you go downstream, you can see the water, the discharge through the channel. And so you can kind of use this to follow the water, the propagation of water downstream. As the water propagates downstream, it collects the water and then it feeds the structure. And you can compare these columns of data with this data. You know, you can just go upstream a few cross sections and compare the two and make sure that your rating table is working good. You can also bring your rating table in there as well. And then if I get down to that Greenway, I think that's Greenway 1. But get down there to Greenway 1. Three, 5, 1, 7. Yeah. Greenway 2. Yeah. This is the downstream one. They're kind of in the wrong order because when I put them in and I didn't go upstream to downstream. It doesn't matter, but just, you know, for the sake of reviewing, it makes it easier. So you can follow this and you can see that we had about 500 CFS. So we were around 2 feet of depth in our channel. And then you can just do comparisons, like slightly upstream or slightly downstream, and make sure that those are kind of in agreement, and check it here as well, and just kind of compare them if you have a structure that you're worried about. Also, another thing you can do on those channel ones is, let me grab something real quick, and I'm almost done. So thank you for bearing with me on this. I'm almost done. So I'm going to grab that. I'm pasting hydrog in here. And then I'm going to paste that grid element number right there. Let me go grab that grid element number again. Nope, it's not there. It's here. I'm going to grab this inlet number and I'm going to put that in this table and click that, and that will give you the see, I put 100 cubic feet per second in this channel, and then this is what's coming from outside the channel. It could be either rainfall or coming in from another structure or whatever. And then if I go downstream, you'll go through the structure. And so what you don't want to see is like this getting super spiky right next to a structure because the structure geometry doesn't match the channel geometry. So if you start seeing spikes coming up to and going away from a structure, it's very likely that the cross-sectional areas leading up to that structure are wrong, and you're probably just drawing this rectangular or trapezoidal cross-section all the way up to the structure. Okay, we are a little over time. I appreciate your time. I'm going to go ahead and stop the recording here.